One of the most important applications and one of the most classical applications of matrix theory is to the theory of systems of linear equations. So here we're looking at a general system of m linear equations with n variables. The idea here is that we're looking at a list of equations where the variables are given by x1, x2, all the way up to xn. So we have n variables. And the idea is that we are scaling each of these variables by some constants, which we're denoting by a's with subscripts here. And then we add everything up and we set each equation equal to some other constant. And on the right-hand side, we're using b's to denote those constants. We call this system linear because with each of the variables, we're not doing anything fancy like squaring them or exponentiating or taking trig functions. We're only looking at the variables themselves. A solution to a system of equations is a vector denoted maybe by x, whose coordinates solve each equation. So we would say x here is a solution if, when we plugged in all of these coordinates into all of the equations were satisfied. So the name of the game is, if you give me a system, can I find solutions? Well, systems that have solutions are called consistent. So a system is consistent if it has at least one solution. So here we have an example of a system of equations. Here it looks like we have 4 equations and 3 variables. And I went home and I managed to find 2 solutions. I found that if you plug in x1 equals 5, x2 equals 2, and x3 equals 0 in the system, all of the equations are satisfied. I also found that if you set x1 equal to 6, x2 equal to 3, and x3 equal to -1, also all of the equations are satisfied. So evidently this system has at least 2 solutions, and maybe there are others out there. But the point here is that the system is consistent because it has at least one solution. On the other end of the spectrum, we have inconsistent systems. Inconsistent systems are systems that have 0 solutions or no solutions. Here we have an example of an inconsistent system of equations. So here we have 4 equations with 3 variables. And the thing I want to point out here is that if we added all these equations together, we end up with the equation 0 equals 1. So if we added all of these equations together, keep track of the coefficients. -5 times x1 minus 4 times x1 is -9x1. But then we add 2x1 and 7x1, that's plus 9x1, so we get 0. If we add 4x2 plus 1x2, that's 5x2, but then minus 2x2 minus 3x2 is -5x2, so that cancels to 0. And then -x3 minus x3 is -2x3, but then plus x3 is plus 2x3, and that also cancels. So if we added all the equations together, on one side of the equal sign we would get 0, and then what happens on the right-hand side, we get 3 plus 1, which is 2, plus 2, which is 4, minus 3, which is 1. So we get 1 on the right-hand side of the equal sign. And this is a problem because 0 is not equal to 1. So it's impossible to find a solution to this system, because if you did find a solution, you could just add the equations together and conclude that 0 equals 1. So this is an example of a system that has no solutions. This is an inconsistent system. So how does all this relate to linear algebra and specifically matrices? Well, there are 2 ways we use matrices to represent systems. The first way that we use matrices to represent systems is through what's called an augmented matrix. An augmented matrix sort of concedes to the idea that the important thing about a system isn't the variables in the system, it's the coefficients inside of the system. So here's how we construct an augmented matrix to represent a system. So the first thing we do is we keep track of all of the coefficients of all of the variables in the system, and we place them into a matrix. So here we see in our system of equations that we have 4 equations with 3 variables. So in our augmented matrix, we will have 4 rows, and then the first 3 columns of this matrix will tell me the coefficients of each of the variables. So the coefficients in the equations for x1 are 3, 6, 2, negative 7. So the first column of this matrix is 3, 6, 2, negative 7. The coefficients for x2 are 7, 0, because x2 doesn't appear in the second equation, 9, 4. So the second column of the coefficient matrix here is 7, 0, 9, 4. And then the third column should be 4, 9, 0, negative 12. And that's the third column here, 4, 9, 0, negative 12. So the idea is that we're ripping out all the coefficients from the system and we're placing all of those coefficients in the appropriate positions of this new matrix. Sometimes when we're doing this, I like to label the first columns of the matrix to remind myself which variable was placed where. Now, the coefficient matrix itself doesn't convey all of the data of the system because we also need to know these constants that occur to the right of the equals signs. So what we do now is in our augmented matrix, you'll see before I box things here, we drew a vertical line. This vertical line doesn't denote anything mathematically as far as the matrix is concerned. It's really for a visual guide for us to remind us where the equal sign occurred in the equations. And so what we do now is we just take all of the coefficients that occurred to the right of the equal sign and place them into the last column of this matrix. So that's to the right of that vertical bar. This is called the augmented column of our augmented matrix. So the idea here is that if you give me the system, I can represent it with an augmented matrix. And conversely, if you give me the augmented matrix, I can recover the system. So what we're doing is we're re-representing, or we're representing the data inside of the system using a matrix. Another way we use matrices to talk about systems of equations is with a matrix equation. It turns out we can use the same data of the coefficient matrix and the augmented column to write down a matrix equation that conveys the information in the system. So this always manifests as a matrix equation of the form A times the variable vector x equals b, where A is the coefficient matrix of the system, and B is the augmented column of the system, or the column of constants that occurs to the right of all the equal signs. Both of these perspectives will prove useful to us. We'll find that augmented matrices are useful for algorithms we discuss, and also matrix equations are useful as we start to learn more and more about matrix arithmetic.